Hello, I'm Elle.
And I'm William, and we are Team Interfair. We're here to present our new tool for intersectional machine learning fairness called the Fairness-Oriented Multi-Objective Optimization Tool, or FOMO.
One of the challenges to fairness is that populations at risk for model bias vary by use case and context. They can be defined by the intersections of multiple sensitive attributes, for example race and gender, such that bias can manifest between black and white individuals or black females and white males, and other intersections of those attributes.
Different situations call for different fairness metrics and different machine learning models. So our design goal with FOMO was to make a tool that would work in a variety of healthcare settings. FOMO supports many common fairness metrics like false positive rates, false negative rates, positivity rates, or fair calibration. And it also supports a range of different machine learning technologies, from linear and logistic regression to random forests to gradient boosting to neural nets and more. One of the primary innovations of FOMO is that it allows users to visualize trade-offs between fairness and accuracy and select the model that best suits their needs. We will demonstrate this now with a model for predicting admissions from the emergency department.
This prediction task has particular relevance to allocating beds in a hospital setting. Many hospitals operate at or above bed capacity, and new admissions from emergency rooms are competing for a finite resource. Poor allocation can result in delayed treatment and potential harm to patients. Prediction models could be used to optimize this process by flagging patients with high likelihood of admission to begin the bed coordination process while the initial evaluation is being treated, thereby saving valuable time. In such a scenario, we would want all groups to be prioritized fairly and minimize bias based on subgroup false negativity rates. We would also want to minimize overall false positivity rates to preserve this finite resource for patients who really need it.
This is a perfect context to apply FOMO. So here we see a baseline random forest classifier predicting the risk of admission. And as you can see, FOMO measures disparities in model performance and outputs the groups that have the highest fairness violation according to several metrics. We can now debias the model using FOMO. So FOMO uses an iterative approach that produces a set of models forming a Pareto frontier, which in our case is a set of models that are the best trade-offs between the overall false positive rate and fairness for subgroup false negative rates. FOMO includes functions for picking from the set, but users can also pick the model that best suits their use case. As you can see from this table, each metric has improved from the base model.
FOMO also saves the training state for the model, allowing users to resume training with additional data to surveil for model drift and maintain fair performance over time. FOMO is open source software, so any healthcare entity, academic medical centers, community hospitals, or research organizations can use it without cost, so the tool can quickly scale within the ML market. We hope that everyone will take the opportunity to use FOMO so that no community or metric is left out.